In an organic reaction, when reactants react to form a new compound, the reactant that supplies the carbon atom for the formation of a new bond or to the reactant on which the focus is called the substrate, whereas the other reactant in the reaction is called the reagent. In the reaction between chlorine and methane, methane supplies the carbon atom to form chloromethane. Hence, methane is the substrate, and chlorine, the other reactant, is the reagent. Covalent bond between carbon and bromine of methyl bromide gets cleaved and a new bond between carbon and hydroxide ion is formed. The energetics during breaking and forming of bonds, movement of electrons, and the rate of reaction in a sequential description are referred to as the reaction mechanism. Let's study each step in detail. A covalent bond can get cleaved either by homolytic cleavage or by heterolytic cleavage. In homolytic cleavage, a bond breaks equally in such a way that each atom gets one electron of the shared pair. A fishhook or half-headed arrow is used to show the movement of a single electron. Homolytic cleavage results in the formation of neutral atoms or groups with one unpaired electron. These are known as free radicals. The free radicals thus formed are highly reactive due to the presence of unpaired electrons. For example, the homolytic cleavage of the chlorine-chlorine bond in chlorine molecules, induced by heat or light, leads to the formation of two chlorine free radicals. Depending on the number of alkyl groups directly attached to the carbon free radical, alkyl free radicals are classified as primary, secondary, and tertiary. Greater is the number of alkyl groups, greater is the stability. Hence, primary alkyl radicals are the least stable, while tertiary radicals are the most stable. The organic reactions preceded by homolytic fission producing free radicals are called free radical or homopolar or non-polar reactions. Heterolytic cleavage is just the opposite of homolytic cleavage. In heterolytic cleavage, a bond is broken unequally, and the shared electron pair goes to the more electronegative atom. Thus, after heterolytic cleavage, the atom that loses the bonded electrons gets a septet, electronic structure, and acquires a positive charge. For example, in the heterolytic cleavage of bromomethane, the shared electron pair goes to the bromine atom, leading to the formation of a bromide anion and a methyl cation. A positively charged carbon with a septet, which is the methyl cation here, is called a carbocation or a carbonium ion. Carbocations are very reactive as they have a strong tendency to complete their octet. Depending on the number of alkyl groups directly attached to the positively charged carbon, Carbocations are classified as primary, secondary and tertiary carbocations. For example, ethyl cation is a primary carbocation, while isopropyl carbocation and tert-butyl carbocations are secondary and tertiary carbocations respectively. Stability of the carbocations increases with increase in number of alkyl groups bonded to the carbocation. Hence, primary carbocations are highly unstable, while tertiary carbocations are the most stable. In methyl carbocation, 3 sp2 hybridized carbon orbitals overlap with the 1s orbital of each of the 3 hydrogen atoms. The remaining 2p orbital of carbon is vacant and lies perpendicular to the molecular plane. Therefore, the shape of the carbocation is trigonal planar. There are also heterolytic cleavages where the carbon gets the shared pair of electrons. For example, the removal of the hydrogen ion in the presence of a base from the methyl part of an acetaldehyde molecule leaves both the carbon-hydrogen bond electrons on carbon. Such a chemical species bearing a negative charge on carbon atom and possessing 8 electrons in its valence shell are called carbanions. Carbanions also are classified as primary, secondary and tertiary carbanions, depending on the number of alkyl groups attached to the negatively charged carbon. Stability of the carbanions decreases with increasing number of alkyl groups bonded to the charge-bearing carbon atom. Hence, tertiary carbanions are highly unstable, while primary carbanions are the most stable. The shape of a carbanion is tetrahedral. All the organic reactions preceded by heterolytic bond cleavage are known as ionic or heteropolar or polar reactions. Polar organic reactions are caused by 2 types of reagents: electrophiles and nucleophiles. Electrophile is an electron-seeking or electron-loving species, as it is electron deficient. Electrophiles may be either positively charged, such as carbocations, hydrogen ion and hydronium ion, or electrically neutral species such as boron trifluoride, aluminium chloride, ferric chloride and carbonyl group. A reaction initiated by an electrophile is called an electrophilic reaction. Electrophiles always attack the substrate molecule at the site of maximum electron density. An electron-rich reagent that donates electrons to the positive or electron-deficient site in a compound is called a nucleophile. A nucleophile is a nucleus-loving species, as it is electron-rich. Negatively charged species with lone pairs of electrons, such as hydroxide, chloride, cyanide ions and carbanions, and molecules such as water, ammonia and lithium aluminium hydride are some of the neutral nucleophiles. A reaction initiated by a nucleophile is called a nucleophilic reaction. Nucleophiles always attack the substrate molecule at the site of minimum electron density. The movement of an electron pair in organic reactions is denoted by a curved arrow. The curved arrow starts from the point where an electron pair is shifted and ends at the final location where the pair of electrons may move. For example, electron flow from a pi bond to the adjacent bond position, or from a pi bond to the adjacent atom, or from an atom to the adjacent bond position may be represented as follows.